So one more time. Yes, sir?
Are you recording this?
I am right now. Just started it. Power functions take this form. You can have a polynomial. You can have rational. You can have radical. As long as it's one of those formats, it's considered to be power functions. And so what we're going to do is I want you to analyze the function. Let's see. So here's two power functions. Here are the things that I want you to tell me as you analyze the function. This is not a short list. Okay? So if I give you two problems to do like this, which is what I've done, it's actually a fairly long process. You may be good at some of these things. Some of these things may be difficult. Some of these things you may recognize. Some of these things you may have never done before. I'm not really sure. We'll find out today. The second thing, of course, is range. Third is continuous or discontinuous. Let's talk about that one for a minute. What do I mean by that?
Like really infinity, or is it negative?
No. The word continuous or discontinuous, the graph is either continuous or it's discontinuous. The easy way to think about that one is if you can take your pencil and you can draw that entire graph without ever picking up your pencil, ever, means it's continuous. But if I've got to pick it up, like for example, 1 over x, it's a rational graph. If you graph it, it looks like this. You graph here, then you got to pick your pencil up and go down here and graph the other part of it. They're not connected. That is discontinuous. In fact, that's discontinuous at x equals 0 because I can't plug 0 into 1 over x. It makes it undefined. So I'd have to skip over that number, meaning pick up my pencil, put it back down, and keep drawing it. If you have to pick your pencil up for any reason, it's considered discontinuous. I mean, it's literally what the word sounds like. Increasing, decreasing. Don't know that? Sorry. Have you done that before? Where's the graph going up? Where's it going down?
No.
Okay. Ms. Schumach was telling me, well, they don't know all this stuff about the graphing and the analyzing, so that's what I need to know. I just need to know what you do and don't remember or have ever seen. I will go through these. Symmetry. Is something an odd function, an even function, or neither one? Very simple test to do that one with. That one's fairly straightforward. You just do the test, look at the results, boom, that's what your answer is. The next part is extrema. I need you to find the maximum, minimum values. Is it local or a global value? In other words, is it the absolute highest point on the graph? Take, for example, negative x squared. Right? Negative x squared is an upside down parabola. It has an absolute maximum. We call that a global max or an absolute max. There is nothing higher on that graph than that. But it has no minimum values. There is nothing. It keeps going down forever. Turn it around. Look at x squared. It has an absolute minimum, a global minimum, but no maximum. Take a cubic function. Cubic functions go up, down, back, up, right? And so you have local or relative minimums and maximums, but no absolute, no global. Because it goes up forever and it goes down forever, never stopping. Okay? Asymptotes. Horizontal asymptotes, vertical asymptotes, slanted asymptotes. Horizontal are very simple to calculate. It requires you to remember some rules. Vertical asymptotes can be difficult, but the method is the same every time, so there's just one thing you have to do. Yeah. ASYMPT. Switch the P and T. Asymptotes. And then, of course, end behavior. These are the things that, when I ask you, analyze the following graphs, here are the 8 things I'm looking for. That's a lot. It is. Okay? So, having that down, no big deal. It's not that you have to memorize what to do. I'm not ever going to make you do that. It's knowing what to do for each one. Okay? So what we're going to do is we're going to go ahead and graph these things. So what I'd like for you to do, if you have a graphing calculator, go ahead and pull it out. If you don't have one today, then move your desk somewhere that you can see one and just share with somebody else so you can see. But really what I want you to do is to look at the picture of the graph. We're going to get that down and talk about it. So I'm going to give you a few minutes. Go ahead and let's graph some of these things. So let's look at the cube root of x first. So now that you can see x cubed, either in your calculator or you drew it by using the xy table, picking perfect cubes and plugging it in, it looks like a very stretched out S shape. What is the domain of the cube root of x? Do we know what to do when I ask you for domain? Domain, if you look at there's a number of ways to do this. Can you think of any number that I can plug in and it would give me error or undefined for the cube root of x? Is there any number that will not work in this? And that's not the best way to think about it, but for cube roots, there's nothing you can't use. Everything works. Negative numbers, 0, positive numbers, fractions, they're all good. I can take the cube root and it might not be a nice number, but it works. So the domain, so number one, the domain is all real numbers. No restrictions at all. Now, the range is a little bit more difficult to go by. The graph really helps out. Look at the graph itself. We just got through discussing number 3. What is it? We said it goes through everything without skipping, so it's going to be continuous. So it is continuous. Number 4 is the increasing and decreasing. All right, this one's a little tricky. For this one's easy. We'll do one in a minute. Wait to think about it. You're looking at this particular graph, and I want you to tell me from left to right, just like you read a book, go across that graph. Act like you're literally walking along the graph, and you're headed this way. You want to tell me where are you going up and where are you going down in terms of the x coordinate that you're on. So this particular graph, if I'm walking along this curve from left to right, which way am I headed? I am increasing for the whole time. So you have no decreasing interval, so it's going to be just increasing, and it's going to be from negative infinity, comma, positive infinity.
So you never go right to left?
You never go right to left. It's always, just like reading a book, left to right, and you always, and this is the big deal, you always give it to me in terms of the x coordinate where you're standing, never the y coordinate. Sometimes it's temptation to, well, I'm going up and down, so I'm going to give you the y coordinate that I'm at, and that's wrong. It's always where are you along the horizontal axis. We'll do one in a minute that's a little bit different than that. Number 5, it is symmetry. There are 2 main symmetry types, evened and odd. Okay, even means it's symmetric. If I could cut the graph right on the y-axis, if I could cut it right through here on the y-axis, then it's the same exact one on both sides. Clearly not the same. One's above the x-axis, one side is below the x-axis. So it's not even, visually. Odd, if I can take my picture and I can turn it 180 degrees and I have the exact same image, that's odd. Odd means point symmetry around the origin. Okay? If you turn this upside down, do you get the exact same picture? Yes, you do. So this is odd. Now let me give you a much better way of determining even and odd. Even, our equation is this, right? What you're going to do, the test for even and odd, I'm going to plug in negative x. And so, what does that equal? It's going to be negative whatever my y value ends up being, right? So technically, the cube root of this is negative whatever the number would be. See how the signs are exactly opposite? Cube roots with negatives work just like any other negative. It's the square roots or the even roots that you have to worry about. because these are opposite signs, it means it's odd. If it's even, nothing will have changed. For example, y equals x squared. Plug in negative x. If it is exactly the same, if every single sign that you had stayed exactly the same, you've got an even function. If every single sign changed to the opposite sign, you have an odd function. If something else happens, some change but some don't change, you have neither. Bottom line. Okay, number 6, Extrema. Does this graph have any extreme points? None. So we write none. So 6 here, we have none. It does have a point of interest, though. Do you know what this is called? On the graph, it is called the origin, but on my equation, what is it? It changes concavity. It's concave this way, and then it changes to concave down when it goes through it, right? The way it's curving up, but as soon as it touches 0, it curves back down. So the bowl is inside here and it's inside up top. It changes positions. It's called a point of inflection. The way that the curvature goes, it's going up like this, one way, and then it changes to this way. When it changes curvature like that, we call it a point of inflection. That's not a critical point or a max or min, but you'll need to know that eventually.
What does the local and global mean?
If you had something like a quartic equation that looks like this, like a fourth power, you have 3 different extreme points. You have a minimum that's a local relative minimum and an absolute minimum. Okay? When you have these types of things, even though both of them are minimum values, one of them is an absolute minimum. One of them is just relatively minimum. In that little local area it's in, it's a minimum value. But overall, globally, or absolutely, the actual minimum is one way down at the bottom. But this maximum, what would you call, is that absolute or is that relative? It's on the relative because look on the sides. Both ends go up to infinity. It doesn't have an absolute maximum. There is never a point that you could tell me that nothing goes above that value because it's going up forever. Does that make sense? You ever asked that question? Yeah. 7. Okay, asymptotes. There's only one type of graph that has asymptotes. You know what that is? Well, yeah.
It's the one with the 2 little...
Rational. Anything that has a fraction with it is possible to have an x in the denominator, okay, which a lot of our conics fit that description, hyperbolas and stuff. We're not going to get there. In fact, we don't talk about conics at all. So in this case, none. If I had a rational, a fraction, which we'll get to eventually next, it is definitely going to have an asymptote. It may not have all 3 types. Horizontal, vertical, or slanted. In fact, you can't have slanted and horizontal asymptotes. It's one or the other. You can't have both. Number 8, end behavior. This is a prescription, actually. You're going to actually write this down as a very distinct method. It's going to be f of x is approaching as x is approaching. You're going to write these in what we call limits. Those of you going on to calculus will see this very often. So really, I'm going to draw the prescription. As x goes to negative infinity, as x goes to positive infinity, what's happening to my y value? That's the way you start off with. And that's the same. None of this changes for your in behavior. Okay? All right here, always the same. So when we're talking about in behavior, it's f of x is going to some number as x goes to negative infinity, and f of x goes to some number as x goes to positive infinity. Okay? So what we're going to look at here is, well, what number does it go to? So this is key phrase for left. And so negative infinity is left, and positive infinity for the x's is right. So as we go these different directions, what's happening to my graph? What's happening to the y value of my graph? So let's look left. As we go left down the x-axis to the left side, what's my y doing? It's going more and more negative, right? The y value is going down, 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 and it's going to keep going that way forever. So what is the limit going to be?
Negative.
Yeah, negative infinity. It's going to keep going down. It's not going to really have a limit. So if you're looking at it and thinking, as I go left, my graph just goes down forever, then you're talking about key phrases for down is negative infinity. Just on the other side, as you go to the right side, what's happening to that graph? Yeah. Up, key phrase, positive infinity. Practice your infinities lots of times. Just keep doing it. It'll eventually come around.
Crazy.
So this is what you call analyzing a graph. Okay, lots of detail. You get used to it. A lot of it's very quick. And so I'm going to let you kind of look at 1 over x squared. So take a minute. Either plot a couple of points or take your calculator and try to graph it, and we'll look at it. For your horizontal asymptotes, you take the denominator and the numerator. You look at the degree of each one. If the degree on the bottom is larger, your horizontal asymptote is y equals 0. Clearly, it's right there. If the degrees are the same, let's say you had 2x squared over 3x squared minus 1. Degrees are the same. It's x squared and x squared. Divide their coefficients. So you'd say 2/3 equals y. 2x squared over 3x squared minus 1. Ignore everything else but the coefficients of the degree terms, leading coefficients. That gives you the horizontal asymptote this way. If the numerator, if the top is bigger, you will not have a horizontal asymptote. None exists, for top degree is larger. Slanted asymptotes are a little different. We'll save those for another day. End behavior. So let's go back to my picture here. I'm going to erase the part that changes what f of x goes to. As I go left and right, what happens to f of x? As I go down to the left, what is it x? What's y approaching? What's it getting closer and closer and closer to? What is that?
0.
What's the x y value? 0. As we go out this direction, it's getting closer and closer and closer to that value. What about this direction? Also 0. They're both going down to the asymptote. They will never touch the asymptote. They're going to get as close as possible. Therefore, asymptotes, horizontal asymptotes, are very, very much related to end behavior. They will play a part in that. So a lot of these things are very connected to each other. So, to review, we did a lot to go through today. We did 1 graph. Well, 2 graphs. Analyzing graphs. Let's see what I had. Yeah, we'll skip this part. There it was. I was not going to do that. I do have something to give you, because I knew I might not get to it today. This chapter talks about direct and indirect variation. Not difficult. If you've never seen it before, it might not be difficult to start with. Go ahead and put your homework up. I need to erase that.
So you play the drums in the background?
Okay, so you got your homework. You've got this. This is we're just going to look through this in the time that we have left.